Sorry. Mousepad I am using to keep the laptop because it is. Hmm? Yes. Yeah. Otherwise, these guys cannot see what I am drawing on the whiteboard, right? And sometimes, please, someone volunteer if I draw something. I just volunteer to click it and send it. Oh, silent. Perfect. Anybody else is coming? Now all around. How about Abhishek sir? Abhishek has joined, I guess. Sir,
Sir, I'm reaching the college in few minutes.
okay.
Meantime, I'm on phone. Yes.
Okay, so you are taking the class and driving. Okay. So let us
Yes,
start.
last mile connectivity. Yes, yes.
Sure. Like, please be careful. Okay. Let me start. Okay. So when we are studying cryptography, it's working. No, it's not working. So. Sure. Mm, share the screen. I think it's shared now. The right screen or the wrong screen? Okay, so what when we say cryptography, it is kind of a basic building block or the silver bullet for security. Whatever we are doing in security, somewhere we are getting these cryptography things, right? And most of the cases we just skip. We really don't want to get inside what is happening inside, what is happening in background. We just know that this thing happens. That's all. Have you encrypted your desktop, your hard disk? Yes, I have done. But I really do not know how exactly the thing is happening. Or are you using a HTTPS? Yes, I am doing that. But what is happening in the background, we do not know. While saying that, uh, which one, like in the top one, like this one, which one, where you will categorize yourself? Anybody understand it very well? Somebody doesn't understand? Or maybe it sounds nice in the beginning, then all of we started reading it, studying it, and somewhere we get stuck, then nothing I could understood, and then I just stopped. And only I know about Alice, Bob, Eve, and some terminologies. And the fourth one is a holistic idea, holistic view I have. So where you will categorize yourself in this fourth? Holistic. So you know proficient, but not an expert, but not a beginner possible. Okay. And basic. But not good. Okay. And what about mathematics? Okay. I'm just ignoring the people on online. So guys, can you please tell me where you belong in this four bucket? First, second, third, and fourth.
For me, that Alice Bob.
Okay, Alice and Bob. Anybody else want to say? Okay. So today my lecture I will keep it in a holistic level only. We'll go in some detail, and most of the cases it is a holistic view. And even though like after some time we will probably forget the detailed things, but what I really want that at least what is what you should know, At least we should know how the things are working, and we should know that okay, this is doable. This is not a magic. It is not a black magic. It is something logical. Okay. And what about your mathematics skill? Like anybody understand discrete theory, vector analysis, and algebra?
Used to.
Used to. Okay.
I had undergone some training for cryptography, so I know some of the things, but I need to revise.
Okay. Great. And remember my school days math. At least this one I can expect from everybody that the school days mathematics plus 10 only. Not I'm not going to those integration, differentiation, all these things. Not calculus. Just the simple mathematics. 10 plus 10.
It is mostly prime number BCD.
Yes. So
Actively.
we remember that thing, right? Yeah. We'll touch. We'll just quickly brush up all those things, and then we'll jump into the main course content. So I can expect that we already know what is confidentiality, integrity, and authenticity, right? Okay. And Kiran, what is the difference between confidentiality and integrity? Just quickly.
How to give it one. Confidentiality is like whatever the data we have, it was not supposed to go outside of authentic use.
Okay.
So integrity is the data which we have is the data exactly what we require.
Oh. Okay. Do you know cryptology, cryptography, cryptanalysis, and crypto system? Who doesn't know any of these terms? Also, people joining online, please please interact. Otherwise, it will be boring for you guys only. Anybody else like any of this?
Idea, but the content of exact terminology is not.
But this terminology we have heard some point of time, right? Okay.
Yeah,
What is cryptanalysis for?
Cryptanalysis is analyzing the cipher text to identify the key used for the encryption.
Okay. And what is a crypto system?
Crypto system is like public key infrastructure PKI system.
Okay.
An overall system.
Okay. We know about plain text, ciphertext, encryption, decryption, hash function, and ciphers. At least a basic idea. We have heard about this.
Yes.
We do not know how. Maybe we do not know how exactly they are working, but at least what they are doing, how they fit into fit into our day-to-day life. We know that, right?
I have a vague idea, but
Okay, we will go. We'll go. The entire day is there. We'll go. And do you know what is work factor, what is entropy, and what is randomness? Okay. Work factor means the time that should take to break a cryptographic algorithm. That is what we call work factor. So, if work factor is more, that means it is a better cryptographic algorithm or it is a better crypto system. And if it is lesser, then it is a worse crypto system. That's how we this is a mathematical measure, or this is a measurement of how good a crypto system is. So we measure with these three things. One is work factor, entropy, and randomness. Okay, entropy and randomness are again interlinked. Randomness, we know what is randomness. What is randomness? That does not follow any pattern. So for any logical, by any logic, I really cannot guess what the number is. That is called a random number. Like if
the number of bits in E.
no pattern. Like I ask you to just guess a number, any number. Give me any number.
Okay.
Just give me any number.
3, 4, 5, 6.
3, 4, 5, 6. You just come up with this number. Okay. Now, without knowing you or how you think, anybody else really cannot guess what number you are going to say. Right? But 3, 4, 5, 6 is not a it is a random number, of course, because it came randomly in your mind. But now comes to entropy. Entropy is a measurement of the randomness. So 3, 4, 5, 6 is actually doesn't have much entropy. It is a random number, but a bad number, random number. Why? Because it is a pattern. 3, 4, 5, 6. It's a pattern. Any human being usually think in that way.
Entropy is less.
Entropy is less. So entropy more, that means it is the randomness is more. Okay. So entropy is the measure of the randomness. And just tell me how a computer can generate a random number. How it can generate?
By algorithm.
Yes, but how that algorithm would work? How a computer can generate a random number?
We can program.
Yes, how you can program? Like what would be the logic? Because you need to, like, if you program, every time you run the program, it will come up with the same number. But what you want, every time you run the program, it will come with a different number with randomness. It will be a random. A human can guess, how a computer will guess. How can I generate a random number in a computer?
So sometimes you hover over the mouse.
Sorry?
Sometimes you hover over the mouse and it takes the
Yes.
random.
Yes. So sometimes if you probably you have come across some such application where it asks you to just move your mouse randomly, and on the basis of that it generates a random number. So that is kind of a human pattern. So whoever is using it is always dependent on that. Is it a good random number? Yes, it is a good random number because everybody in the world will have a different type of mouse hovering. Or another one might be is the time. Time always changing. But that is not a good random number. Why?
Entropy.
Entropy is less because I can guess when you have run it. At least I can get a range. By this range to this range, you have the random number will be. So time can be used. In fact, most of the algorithm, the previous older days algorithm, to generate random number, it used to use time. Nowadays, that mouse hovering, the user interaction is there. So that's why, like when we use a constant seed, so these are called seed, on the basis of which I will generate the random number. It might be time, it might be date, it might be your location, all these things. So these are called seeds. So the seeds, if I can guess the seeds, if I know the seeds, then probably I can find a range. Okay, this will be between this range, right? So that's why we call it a pseudo random number, because if whatever you do on your computer, somehow people will guess that what would be the seed. So that's why we call it a pseudo random number. But if I ask somebody to tell me a random number, if he is a very rational person, he would give me a number which will really I cannot relate with anything. It just comes to his mind. Again, people argue this might be a pseudo random as well. If I know that person very well, I might guess that what the way the direction is thinking. Okay. So this is called randomness, and random number is very important for our cryptography. I will come to that. And we all know Bob, Alice, and Eve. We know their stories. And cryptography. So it came from cryptos, that means secret, and graphy means to write. So how to write a secret, that's what a cryptography. So cryptography is a study of hiding information. How I can make my information secret. That's what we call cryptography. So this is the definitions. When okay, cryptology. So what is cryptology? That is probably we stumbled upon that. What is cryptology? Cryptology is cryptography and cryptanalysis. And cryptanalysis, what you define, what it would like a little bit different from that. Cryptology is breaking a crypto system. How I can break a cryptography, how I can guess the key, how I can guess the plain text from the ciphertext. That is what we call sorry, yes. From the attacker side, or I would say mathematical view, because most of the cases when we come up with a new cryptographic algorithm, we need to prove that this is good. For that proof, we need to provide the cryptanalysis. Okay. So how I can break a crypto system? How from the ciphertext I can find what the plain text is without knowing the key, or if it is a asymmetric key cryptography, just using the public key and the ciphertext, can I guess the plain text? Can I guess the key? All these things are part of cryptology. And cryptography is a technique for secret writing, and crypto system is the implementation of cryptography. Okay. So now things are clear. What is cryptography and crypto system? Crypto system is the implementation. So AES is a crypto system because we have implemented it on in a code, right? It is also a cryptographic algorithm. It is also an algorithm. It is also a crypto system. When it is in a logical sense, I am telling you like a pseudocode or just a flowchart I am drawing, or the logic I am giving. That time it is the algorithm, and once I implement it in a code, C code or Java code, whatever code, then it becomes a crypto system. Makes sense? And cipher is the basic building block of that implementation, which performs the encryption and decryption algorithms. Okay. So this is the basic building block of crypto system. So if I think of a crypto system, it will have a lot of basic building block. One of the building block is how I will implement the crypto system. Like you can just think in the object-oriented programming kind of thing. So if I implement a crypto system, that means it should have a encryption algorithm. I have to first implement the encryption algorithm, that is a cipher. Like encryption and decryption, or if it is a hash. So all these things, the basic building blocks, we are calling ciphers. We'll come to ciphers. What is ciphers? We'll see different type of ciphers. We know what is a plain text or clear text means. We know cipher text, or it also has another name called cryptogram, though nowadays it is not used, but initial days cryptogram, this word was more popular. Okay. Actually, I think this came from a very famous writing from Alan Poe. This cryptogram also, I think 100 years back he has written a short story and kind of a sci-fi story where he used this cryptogram. Anyway, and encrypt, we know what is encrypting, like making scrambling the data in such a way that nobody can find out what was the original data. So making cipher text from plain text is encryption or encrypt. We also call it encipher, but encode is little bit different. Encoding means, yes, we are scrambling the data, of course, but the main intention is not to hide the data. That's why it is easy to decode. You don't need anything to decode it. You just need to know the algorithm. If you have the encoded version, you can decode it, right? Similarly, decipher or decrypt is the word. Decode also is there. Now, encode and decode has a different meaning, but initial days, people also used to use this term, encode and decode. But now, encode and decode has a different meaning. Cryptanalysis, as I said, it is a practice of breaking the crypto systems and the work factor, time, effort, and resource necessary to break the crypto system. Perfect. Now, things are clear. People on Microsoft Teams, please make some noise.
Clear, sir.
Okay. Actually, I really do not know who is speaking. Okay. So you guys are with me, right? So far it's clear. There is nothing to be confused. Is there anything to be confused here, or everything is fine?
No, good.
Okay. Okay. Now let's go to the next. Now, what is a key? What is the key? How can I define a key? So it is a secret, some secret. That secret is only known to the person who is encrypting or to the person who is decrypting. So that is the only secret. So if I really want to keep a secret, then why I cannot keep the entire text secret? The reason being, the entire text might be a very big, but when I'm talking a secret, it might be a small piece of information. So a small piece of information I always keep secret. I do not know how I can keep it secret, but I have to keep that piece of information secret. If I can keep that, then the entire crypto system works. If I cannot make that small secret, then I cannot make a bigger text secret. Okay. So this is a funny thing. To make something secret, you have to maintain a secrecy. Okay. And key clustering, it is kind of when two keys generate the same cipher text. Yes, it happens sometimes. It is logically possible. It might happen. because it's all dependent on the random number. Somewhere, it might be possible that two different keys, but they are producing the same ciphertext. Okay? And key space are the all possible keys. Like if I am using 256 bit of key, that means 2 power 256 is the key space. Got it? Got my point? How 2 power 256? Say I have a 4 bit of key. 1 1 0 1 1 1 0 0 1 1 16. So total 16 possible keys I would have.
2 raised to 4.
Sorry? Yes,
4
2
with 2 raised to 4.
2 power 4. So I will have totally 16 keys if I use a 4 bit of keys. Key. If I use 64 bit of key, 2 power 64 number of keys. If it is 256, 2 power 256 bits of keys. Understood, right? So that is what we call key space. So if it is a 4 bit of key, we will only have 16 keys. If it is 256, 2 power 256. Initialization vector will come to that. It is another random number which is not a secret. It can be shared with anybody, but still we need it. Another random number which can be public. I don't care whether it is public or it is only known to me, but I have to make sure the encryption and decryption both ends should know that the same initialization. That is the only thing I care. But if rest of the people also know, I don't care. I only care about the key to be secret, nothing else. Okay. So this is the thing. Cryptology is the entire study of cryptography and cryptanalysis, anything related to the crypto. Then cryptography has 3 different types of cryptography we know. One is symmetric, asymmetric, hash. I guess all of us here, we know what these 3 types of crypto systems are, right? Guys who are online, please sometimes make some, like, please speak sometimes, otherwise I will really forget you guys. Yes, no?
Yes, sir.
Yes, sir.
Okay. And people who are watching Netflix, please switch off. Okay. And symmetric cipher, like symmetric cryptography, will have usually use 2 types of ciphers. One is stream cipher, another stream cipher, and the block cipher. Will come what. So this is the holistic view. We know this is the secret. Like Bob knows one key, and he can encrypt "Hello Alice." It will be a scrambled up data. Nobody else in the world can find it unless they have the key. So for the symmetric key cryptography or private key cryptography or one key cryptography, these are the 3 names here for you guys. These are the 3 names. Can I use this one? I believe this one would be useful. So if there is one single key which is used for encryption and decryption, we call it as symmetric. If there are 2 different keys, one for encryption and another for decryption, then we usually call it public key cryptography or asymmetric key cryptography or 2 key cryptography. And there is something called a hash function, which is a keyless. There is no key. So far, fine. I'm just like, these are the very basic things I'm right now covering. I think everybody knows. I'm just making a refresh on that. And one more thing I just want to say here. Everything is numbered. Do you understand what does that mean? Everything is a number. What does that mean? So in your computer, if you are watching a movie right now, then that entire movie is nothing but a very long string of zeros and ones, an endless stream of zeros and ones.
Yeah.
If it is a picture, it is actually a finite number of zeros and ones. If it is a text file, it is also a number of zeros and ones. It is nothing but a streams of zeros and ones. And if you write zeros and ones, that means it is a number. It is a binary number. It might be a very long, even a 4 GB data, that is actually a very big number. I guess this one. Okay. 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 So now it is clear that everything is nothing but a number. If it is a long string of zeros and one, that means somehow we can convert it into a decimal number. It is a very big number, but a number, right? Even the entire AWS, the entire cloud, the entire Google cloud, whatever, everything that is also just a long string, a very long string of zeros and ones. That is also the entire AWS might be a number. Right? Entire www might be a number. So anything is a number. A software is a number. So now, if I can encrypt a number, or if I can scramble up the numbers, that means I am done. Because every piece of information is nothing but a number. And Claude Shannon was the guy who actually first told that everything is a number. Whatever we are speaking, all information can be converted into numbers. That's what the Claude Shannon said. And like he is the father of the information theory. So that's why everything is a number, and that's why if I can somehow apply some mathematical function on this, I'm done. Now things are easy. Mathematics, there are a lot of mathematical functions. We really cannot apply a function on a text, or we cannot apply a function on what I am speaking. But on a number, I can do. Since everything can be converted to number, we can apply this mathematical. What's happening? Exactly. So just don't lose track what we have discussed so far. We know cipher, we know encrypt, decrypt, hash. We know hash, symmetric and asymmetric cryptography. Now we also have come across these Hebrew terms like AES, DES, RSA, MD5, SHA-256. All these terminologies comes. So these are different type of cryptographic algorithm, and when that cryptographic algorithm is implemented, that is a different type of crypto system. Sometimes they are the cipher. That means that entire crypto system has only one building block, which is the AES cipher. So AES crypto system might have only one single cipher, which is AES cipher. Okay. Now we know what is cipher, what is crypto systems, and what is cryptography, and what is an algorithm. And MAC, digital signature, TLS, PKI. These things also we know, but we'll go into details what they are and how we can use them. FIPS 142 is the standard that we use for cryptography. So you really cannot cook up your own algorithm or own cipher, and you cannot use it in your application if that application is a public one. It has to follow some standard, and this FIPS says that these are the cryptographic cipher you can use, these are the things you have to use, this should be the key size. All these things are standard across industry, and you have to follow these things. Otherwise, anything like you really cannot write your own algorithm and implement it. That will eventually be broken unless you are a mathematician and you know you have done the cryptanalysis and you have proved it. Okay. Steganography, okay, Vijit will discuss about that. We'll also discuss about the post-quantum cryptography, a little bit maybe, and the blockchains also. Blockchain, is there any other classes where blockchain is covered?
No.
Okay, so we'll also keep some time for the blockchain. Okay, what is the blockchain, how it works. So crypto nowadays, like 3-4 years back, crypto means people used to understand it is a crypto system. Now crypto means people usually understand it's money. Okay. Currency. So yeah, we'll just discuss about a little bit of cryptocurrency and why we are calling it crypto and how crypto is actually building that money, and whether this is a money or not. That also we'll discuss. So this is kind of today we'll cover, not today, probably we'll cover somewhere till asymmetric, then next day we'll discuss the next of the thing. But we'll cover symmetrical cryptography, hash, and little bit of asymmetric cryptography. Okay. And when we are covering symmetric key cryptography, we will discuss about the different type of ciphers, DES, AES, and DPL. These are the things we will cover. And there are a lot of other algorithms, other ciphers. We will just touch. We will just give you the name. If you want, you can actually go into details how they work and all. But cipher DES and AES will discuss in detail how exactly they are working. Probably, I believe, even if you have tried it before, it was not very much clear. If I'm not wrong, because this requires a little bit of hand holding to understand these things.
DA algorithm is very symmetric.
We'll come to that. It is this algorithm is part of the crypto system, but it is not a cipher.
Key symmetry is nothing but both the
We'll
sides.
see. We'll find out the difference. Okay. So this is today's menu card. We'll discuss about the ciphers, how symmetric key cryptography works, provide how we encrypt and decrypt, will provide how the integrity works, MAC and hash, and difficult math. Also, we'll do some basic maths. We have to refresh some basic maths so that we can understand the rest of the things. And a little bit of history, because we'll start from the history. We'll understand that how historically people used to work, what was the problem, and how we are solving it today. Fine. This is probably the next day's menu card. So next day we'll discuss about the ciphers, again regional ciphers. Regional cipher probably today we can cover. Asymmetric key cryptography, how it works, and also how that encryption decryption works in asymmetric key cryptography, and most importantly, how the PKI works. Now let's come to the history. So far clear what exactly I am going to cover today. I'm giving a stress on this because I just don't want you to lose track. That what fits where. Okay. Okay. Let us start with the history. Fourth, like hiding information is kind of an art that people always wanted to follow. Till the human was born, human started communicating with each other. Probably this tendency to hide my information so that some people or the receiver will only understand, rest of the folks will not understand. In fact, I don't know whether like just off track discussion here. Have you guys ever read that book *Sapiens* by Harari? Yuval Harari. It's a very famous book. People on Teams. Have you read? Have you had a chance to read that book, *Sapiens*?
No, sir.
Okay, it's really a very good book. In fact, it's a history book, but it is probably in the last 3-4 years. This whatever books I have read, this is probably the best one so far. In fact, I'm like this is the third time I'm reading the same book. In fact, it has a sequel which is Homo Deus, which is related to this cryptography and the algorithm. So it says that how the human evolved, and there he said a very nice point. Why we can talk, but the beasts or the sheep cannot talk. What is the necessity that human had that the other animals did never had? So there was a necessity that is why nature evolved us to speak, to communicate. So what was that necessity? The necessity was it's beaching. Only human can do that. Dogs cannot do it. Okay, it's beaching or something like I want to say something bad about somebody who is not here. I just want to discuss gossiping. Why we didn't gossiping? Because for sheep, it's very limited vocabulary would work for them. Tiger is coming, danger is there, fruit is there, food is there. Limited vocabulary works because it has only 20-25 sheep in a group. But for human being, they are the weakest one. They are of course weaker than the sheep. They cannot fight a sheep to fight for a food. So that's why they have to come into a bigger group. That's the like, even though human are the best creature on the world, but if a sheep and a human being has a duel, probably will always bet on the sheep. Human will never win. But if it is there are 5 sheep and 5 human beings, still the chimps will, the gang of chimps will, chimpanzees will win. If it is 20, then also chimpanzees will win. But if there are 2,000 human beings and 2,000 chimpanzees fighting, then the chimpanzees will will lose because they cannot collaborate with each other because they do not know how to communicate. But human needed that because human were the weaker from the others, so they had to come in numbers. That's why they can get the food. That's why they can hunt. Otherwise, they really cannot hunt. And since they have a very bigger group, they need to talk. They are sharing same food. They are sharing, partners between themselves. They are sharing the shelters. They are sharing the clothes. That means they have to gossip, and that's the. Otherwise, they will be the weakest link in that gang. That's why we started communicating, and that's the very point where also we started hiding information, or we have started cryptography. So it is communication and cryptography actually came as a brother. Like they invented almost in the same time. Okay, so there are very many such nice things in that book. If you like, it's a very nice read, and the English is also very good. After many years, I have read a book which has such a fluidic language. Sorry. It's thick, but they will not feel bored. It has lot of new food for thought you will get.
Audio, it is 15 hours of listening.
Okay.
So 15 hours is too much.
But it is what you can just like check. It has very nice things they have covered. Okay. So what I was telling, that communication and cryptography came almost in the same time, and say what we have the evidences we have. We got the evidences only 4,000 years back when people used to use this kind of thing. So that time, how people used to speak and how they used to hide the information, we do not know because nobody has preserved their voices, right? But the evidences we get is always in the writing. That's obvious. So that's why 4,000 years back only we have found some evidences where by that time people human has learned how to write scripts. Scripts were already invented, and this is something they used to use. So just think, do you understand what is this? This is called a scythe, I guess. If I'm not wrong. Scythe. So this is the entire string is written in this way. Hello. This is, so instead of writing this one, so this is writing in a, they have write in a ribbon, HELLO, and then tie that ribbon with this kind of a cylinder, and then they take this, only these things, this. So instead of saying hello, it might be like HLLOL, something like that, or E. So you cannot. It is kind of a jumbled up because it depends on the diameter of this. It depends on the diameter of this cylinder where it will come. It's a very simple one, but we know how to decipher that because we have played a lot of this jumbled game. The words, the letters in a word is in a jumbled form, and we have to guess the word. So that is the crypto analysis, and this is the cryptography. Right? 2,000 years ago it worked. 2,000 years ago when Julius Caesar was there, so we had something called a Caesarian cipher, Caesar cipher. And of course, war and battle is the things where we usually used to use this cryptography a lot. So cryptography has been used in two cases. One in the battle, second in the between the lovers. That's the main places where the cryptography has been used. Okay, so in the battle, what Julius Caesar used to do is this is also a very common thing. Say hello, but when this information was sent, they said 2. That means what is the 2 letter away from H, like A, B, C, D, E, F, G, H, I, J. So here is H. H plus 2 will be this one, right? Right? So here also, probably E is getting it is replaced by B. B is replaced by A.
Every second or third number.
Second, third, so that is the key. So this is the key. 2 is might be key, 3 might be key. But with the key space, remember all possible keys. The key space will be 0 to 25 because there are 26 alphabets. Though I don't believe they used to communicate in English.
Substitution.
But let us assume in Latin also there are only 0 to 25 alphabets. Sorry?
Like substitution techniques. One letter is substituted.
Substitution, yes, substitution. Yes, it is a substitution. Okay. So this is the key space, and using the key, I can get the letters. Simple. This is a cipher. This is a very well-known cipher. This has been this was used for almost some 400-500 for 400-500 of years. Okay, but this used to work because probably those time soldiers were dumb or no, I don't know. People could not understood, but now if it is given to us, probably we can. It's not a very. It will not take much time for us to decipher these things. We'll somehow get the key. We'll know that. We'll find out the key. We'll get the pattern, and we'll get the information, right? But it was there. It was very popular. In 200 BC, there is something called substitution cipher by Durvadha. It's Chanakya. So Chanakya in his Kautilyam is the book, I guess. Kautilyam Arthashastra. So there he has mentioned about something called Durvadha. That means how to scramble up the information. How I can do these things. So substitution cipher means usually any letter will be randomly, like there will be a table. First, they will create a table and they will say A will be replaced by X, B will be replaced by G. So some random things they will write for all the 26. So this is kind of a permutation between these 26 this permutation, 26 alphabets. Sorry guys, I am using a whiteboard here. Probably will soon get that picture, because that's the easiest way for me to explain some of the things. So, can I use it here also? Should I use it here?
You can use the Microsoft Whiteboard.
I can use this one as well.
Microsoft Teams Whiteboard.
Okay, so substitution cipher means where it is. Okay, substitution cipher means say A is replaced by some letter, some random letter, maybe X. B is replaced by O. Really difficult. Either we should all go on in online mode, or or the camera should work. It's working now. They are working on it. Okay. Okay. Or should I start my camera here? That also serves.
Your camera, then you have to stand there only. You cannot move.
No, I will just keep it here so that they can. Clarity that we can just try. Otherwise, writing here is also difficult. If I'm online sitting in my home, then it is easier for me to just use the whiteboarding. But Just let me try if it works.
You try it again, but it is that.
Okay, somebody can just rotate the laptop, or if you have a webcam, just check a webcam and then put it somewhere in the front, maybe with the box. Yeah.
I turn on my camera.
Yes, so let him bring the webcam so that webcam can be focused. Right? So in that case, we can at least use this white. Okay. So guys, you are still with me. You understood what I said so far?
Yep, yep, yep.
Okay. So the substitution cipher means A is replaced with a random letter, B is replaced with another random letter, and it will be kind of a permutation of 20. Sorry.
I don't know. Nowadays, the substitute techniques is replaced by only letters or either with numbers as well.
You can replace it with number, but things are same, right? Actually, A is also not A. This is just a number.
Yes.
This is just a number. A is what? A is probably 65. B is 66, right? These are also numbers. Oh, perfect. So anything is number. If you just think in the number way, you can convert the plain text into number and then do the submit, create the ciphertext. Or yeah, but
in
if you
scenario we can use what is called exclamation mark at the rate. Okay.
factorization,
Yes, sir. These things. Special characters. Yeah.
those are encoding, right? Those are really not encryption. Here, this
No,
is
no,
the
not. I'm not saying that encryption, sir. I'm saying that can we use them as a substitution like in this method as well?
yes, you can substitute anything. So exactly what Chanakya substitution cipher was like this actually. Okay, let him bring the webcam. Sorry. Substitution table. Because A is X, B is Z. So that particular data that should be protected. That should be protected. So this is part of the crypto system. This is not the key, but this is the crypto system. That should be protected. You are right. In fact, the previous Durvada was much more simpler. It is like writing. This way. The most primitive one is like C D E F G H I J K L M N O P Q R S U V W X. Sorry, what Y and Z. So it was actually just split it into two, and A will be replaced by M, B will be replaced by N, O will be replaced by C, something like that. So the Chanakya didn't know English. He used to know Sanskrit. In Sanskrit, what they do, you remember in Hindi also or any other language also, there is something called Shravan and there are two vowel and consonants.
Vowel and consonant.
Okay, so this vowel and consonant he actually replaced like the replacement used to happen between the vowels and consonants. So that's how he actually created this one. Later, this table concept came that which will be more randomized, so it will be more secure. So that's what our Chanakya has made. Also, the same cipher was used like used by another great sage of that time called Vatsayana. So don't judge a person by only like don't judge a best-selling book author by only one book. He was a mathematician as well. Okay. Okay. So this is also called Vatsayana cipher. Okay. And now after that, like till the ancient age, these primitive ciphers were good. It was these things used to be used in the war and battles and everywhere. First, the mathematical background of these crypto systems. Which crypto system is good, which is bad, which can be easily deciphered. All these things, all these mathematics behind that. First, people started working on that in almost 800 AD, so 1000 years back, like 1000 to 2000 years back. And that time, like 1000 to 1000 years, 1000, 1200, 1500 years back, the mathematics was only one place in the entire world. Probably people were much more concerned about mathematics was the Arabics, right? And if you know algorithm is actually came from Al-Khwarizm. Al-Khwarizm was a great mathematician of that time who actually said, okay, whatever mathematics we are doing, we can actually split it into small part and we can make a repetitive move and we can come up with a solution. That's why this algorithm word come. Okay. So that time, Arabians, they had an advantage. They had a connection with the ancient Oriental part, ancient India, ancient China. They also had a connection with the ancient European, Greek and Roman. So they could connect them. They had access to all these information. And that time, after that Ottoman dynasty came up in Constantinople, like this Turkey area. So that time it was kind of a very big thing. And mathematicians, most of the modern days mathematics is probably contributed by those Arabic mathematicians. So here also in the cryptanalysis, first book of cryptanalysis that we have found, written by Al-Kindi, an famous Arabian mathematician. Okay. So he first tried to find the mathematics behind that. He first tried to find how mathematically or better way to approach. Yeah, please. Your laptop we can blend it. Yes.
Shall I choose it?
Screen is stopped, but I can see clearly.
But with the screen share, it is small.
Or you can, if you have turned this one, people can actually focus on your video also. If you click on your page, they can focus. So anybody wants to see the whiteboard, they can focus. Like they have to click on parts. Yeah.
Yeah, no, I can always.
Okay.
But issue is the light switch.
Yeah, that we can just little bit
There's a flickering, so yeah.
But
After these two. Better? Still not better. No,
okay. This
so lights.
the reflections, right?
Reflection.
So please take out this. Yeah.
So the other one you can switch on.
Now it is gone.
It's better in it. This will come up.
Yeah, this one also.
It will adjust to light for few seconds. Now it's a little bit better. Can you please
But what is
adjust?
written, they are not able to see what is written.
No, no, no.
It's not visible, but there is feel good about it.
Is it better here?
It's just that the clarity is not that very good. It keeps constantly adjusting. Anyway, so they will
I
understand
think
something.
if it is maximized.
For every few seconds, it's keep
what we get.
important trying to for better resolution.
Fine or
Yeah, it is fine. They need to zoom in or maybe maximize my video because it is very small now. But they can,
your spotlight.
they can see either PPT or either.
Okay. Okay, yes, I am. When I'm coming to the blackboard, anyway, your attention is also coming to the whiteboard only. Okay. So guys, you are fine now. At least you can see something. And
Yes.
you might be like to write it in a bigger script, in a bigger font. I will try to write in a bigger font. Okay. Okay. Now, in the World War I, the Varnam cipher was used. Okay. This is a more mathematical approach towards this. Varnam was an engineer who actually tried to make a different type of cryptography, which is till date we consider it is unbreakable if it is implemented properly. In fact, the Lorentz machine that the Germans used in the Second World War also is an implementation of this Varnam cipher using the rotors and mechanical devices. Fine. So Varnam cipher is kind of a OTP or one-time. It's type of a one-time pad. How they are using, but by this time, like last century, we already knew that everything is mathematics, everything is number, and we know a lot of mathematical operations to work on, and we know how to use that. We have a mathematical background, and that's why this Varnam cipher was probably the first cipher that is kind of we thought is unbreakable. And this is the most famous one probably, Enigma machine that was used by the Germans in World War II. And this is probably the mother of today's computer. Today's computer probably would not have come if people would not have tried to break the cryptography, like break this cipher text from Enigma machine. Exactly. So, how many of you have seen this movie, The Imitation Game? Okay.
Wonderful movie.
Okay. And people on Microsoft Teams, how many of you have seen this movie, The Imitation Game?
Yeah, we have seen it.
Yeah.
We have seen it.
Okay. Many of you. Okay, this is then the people who have not seen it. For their the second like today's first assignment was this movie.
So we can have 5 marks also.
Yes.
Or it is an option of the.
No, it is 5 marks. Yes. There are two movies. This one,
Doctor Strange.
this one, Imitation Game, and the Beat Player. These are the two movies. This is the second assignment. You have to watch this movie, and we'll discuss in the gym. Okay.
Give us more assignment like this, sir.
Sure. Sure.
So if I will join.
Okay. So a little bit history here. Lorentz machine was as I said, this is the implementation of this Varnam cipher. And Lorentz machine was really unbreakable, but still it was broken in 1941. How? Because one thing the mathematicians always told, do not reuse the rotor curve position. Never use that. If you do that, it will be broken. And surely the soldiers, and especially the German soldiers, they are so confident about themselves, they actually use the same thing. They like the same rotor. In fact, only from one single script of 5,000 words was sent, and it was intercepted. But of course, the Allied force did not understand what it is. Okay, how it works first of all. So depending on the different, this is a substitution cipher only. Similar type of these things, the cipher substitution cipher that we have discussed. But since now we are thinking about numbers, numbers are infinite, right? The problem with the alphabets where we have only 26 alphabets, so finite number. We can always find the permutations between them. But when we are thinking about number, it has infinite possibilities. So that was the first thing that actually made it unbreakable. Second, there are so many different keys. So now the key is not only 0 to 25. There are so many keys. Each of these rotor you probably had 30 such like rotor has 30 different what is it, the shafts. Okay. So depending on that, every time you press a letter, depending on this on the position of these rotors, it generates a different number. Okay. And that's how it used to work. And even though it was always told that never reuse this rotor position, that 5,000 word later, 5,000 later message was sent The receiver did not understood that one. Probably some of them things were missing. So they again asked, please resend. And that time, the German soldiers forgot to change the rotor position. So they use the same key. They just thought, okay, we have already said they have spent some time how to decipher that. Let's use the same key so that they can quickly find it out. So they just said the same thing. And the people who are intercepting, they have now 10,000 letters message with the same key, and quickly they just decipher. Okay, this is how we deciphered Lorentz machine. Enigma machine was not as strong as Lorentz machine. Enigma machine was actually a weaker one, but that is more popular because this Lorentz machine used to use, like, it is a very big, heavy one. It was stationed in the headquarters. But the Enigma machine, the people can carry. It is a very small one. It is directly send the message using Telegram. So that's why, like, Enigma machine could send the message in Morse code. So that's why it was much more popular, and it is like you almost kind of a ubiquitous thing. Everybody could use. All the Germans or troops used to use that, and that's why, like, but it took longer time because that their people did not use the same rotor positions. Every time the password got changed. Okay. And who are these guys? These black and white guys. This is Alan Turing, who found, like, how we can decipher the Enigma machine. So the mathematicians were invited. They were like employed to decipher that. And these guys said, okay, I will take a different approach. I'm not going to do normal cryptanalysis. What I will do, I will create a machine, and that machine will find out how many different possibilities, like all the possibilities I will find. So cryptanalysis used to do this kind of thing: 1, 2, 3, 4. What could be the actual message? We just try to guess, and then the next one, say 4, 5, 7, 8, whatever. Then it guess whether it matches. Now the problem with the Lorentz machine or the Enigma machine, every time the password is changing, so this pattern is also breaking every time for every message. That's why it was really very difficult. It really made that Allied force crazy, that how we can decipher the message. How we are getting all the messages. They are sending a radio, and we can intercept everything, but still we cannot understand. Then they just went crazy. That's why the mathematicians were employed, and they just thought, okay, we can put like thousands of mathematicians, they can just try to build. And the Alan Turing first said, no, this is not a possible way. Every day there are 2,000 messages, and by the time all these thousands of mathematicians come up with that with the plain text, the new message will come. We cannot break it. So we have to find the pattern, and that pattern human being cannot find. We have to do it using machines. So all the possible scenarios, the machine will parallelly process. And that's the concept of computer. Computer does that. Not parallelly process, sequentially process. Sorry. So that's the concept of computer. That is the very idea from where Turing also got the idea of Turing machine. And that Turing machine is nothing but today's computer. Right? So computer also came with this like, war has a lot of bad things, but some of the good things are these. We got our computer today. And this is in the Bletchley Park. If you go today in near London, Bletchley Park, you'll still see these machines. So this is the first machine, first computer. Like, it is that time the computer word was not there. Word was there, but it has a different meaning. So this guy Alan Turing first came up with this thing, which is like the mathematics will be done by machine. So people initially never believed him, but later this was the main thing that actually had reduced the war at least by 3 years. That's what people say. Okay? Because now all the moves by the German troops are known to the Allied. It's easier for them to win. This guy was his PhD guide, von John Neumann. Have you heard about von Neumann architecture? Have you ever heard this thing? You have gone through the computer architecture course, architecture or computer organization course, operating system. So this is the guy who actually came up with the first computer implemented. So it was Alan Turing's idea. He implemented it well in something called ENIAC machine. And ENIAC and EDIFAC was the first type of computers, and this is the guide. And till date, we use the same architecture for the computer that the von Neumann came. That's why all the computers that we are using, if you have gone through that memory organization in computer architecture book or in the operating system, we use the same von Neumann architecture. Okay. This is Shannon, Claude Shannon. I just mentioned about his name before. Like, he's the guy who invented how to convert an information into mathematics. What is the information? So first, mathematical analysis of information, information theory, how a machine can communicate, how a machine can process the information, all these things. So the mathematics behind that. So everything will be number, how we can convert everything into number. In fact, it was said that this guy was actually autistic. You know autistic, right? So this guy was autistic and he could not count more than 2. So he actually made all his mathematics subject, and like because he could not, I don't know whether it is 2 or something else, but surely 10 different digits he did not like. He said it is making more complex for me. Why we did 10 different digits? So that's why he actually probably as a play, as a game, he started doing it in the converted into binary and all. Then he became a very famous mathematician, and that actually was one of the influence he had because he was autistic. So that influence he had, and he actually come up with a name when he was uh, researching on the information theory. He actually said, okay, binary is the best way that the machine can operate because it can be either in on state and off state. Okay, and this is Konrad Zuse, this gentleman here. He is a German scientist. He also tried to create a similar thing. Oh, this is Lorentz, I guess. This is not Konrad Zuse. This is Lorentz. So the same Lorentz machine that we are discussing. Okay. Now we know the history behind that, how we came up with computers, how we started sending information, hiding the data, and the question comes, what is a good algorithm then? How can I find a good cipher? What is the best one? Here in 18, like this time there was no war, but this is the same thing that Al-Kindi has started, that mathematically analyze the cryptographic things. This guy Kirchhoff, I think Claude Kirchhoff. So he has given a principle that how I can mathematically convert a plain text into a cipher text, and what would be kind of unbreakable things. He said, system is completely known to the attacker. Let us start with the assumption. It is completely known. He can find out how the system works. So this kind of table will not work because this table someday it will be found by the attackers. Okay. And the encryption and decryption algorithm should also be known to everybody. Okay. Only secret will be the key, nothing else. So the only secret will be the key. Everything else is known, everything else is public. Then if this crypto system works, then we will call it a good crypto system. Fine. And this assumption was made because algorithm will be leaked today or some other day. If there are a lot of mathematicians working on that, they will someday find that what is the algorithm, and they can reverse engineer it in system. That's how the Lorentz, that's how the Enigma, everything was reverse engineered by the people, by the Allied force. But still they could not find because the only unknown thing was that key, the rotor position. That's why it was difficult. Other rest of the things, this substitution cipher, scissor cipher, everything, they thought, okay, I will create a system in such a way that system probably will not be understood by anybody else, but people will understand. So that's why this Kirchhoff principle is very important when we study about modern day cryptography. This is kind of the main principle where on which modern day cryptography is built on. And this is not, he has not come up with this thing on randomly. He has mathematically proven this is the only way to achieve security. Then came this Claude Shannon, who said about perfect secrecy. What is the perfect secrecy? Now, when we are talking about Shannon, we already know that everything can be converted into binary. Everything is a number. This guy said, okay, every bit of key has an equal influence on the ciphertext. What does that mean? That means if I change one single bit, the entire ciphertext will change. It's not a part of the ciphertext. The entire ciphertext should change. That is the principle number one. The second one is plain text and ciphertext should be independent. That means from the plain text, without knowing the key, I cannot guess the ciphertext. From the ciphertext, without knowing the key, I cannot guess the plain text. These are the two big things he has given, and this is because he is the father of invention theory, information theory. It's kind of info how to make that information secret. These two principles are the kind of a prime thing. So Karkaps was the most primitive one, like the first one, and the second one is given by Shannon. It is mostly on the binary data, and these are the two principles all our crypto systems follow. It has to be. And if this is followed, he said perfect secrecy. If it is followed, we'll call it a perfect secret. This crypto system is unbreakable if we can follow these two rules. And he said there are two ways to achieve this: confusion and diffusion. Confusion is binary digit of the ciphertext should depend on several parts of the key. As I said, it is a dependence. Confusion is a dependency between key and the ciphertext. If one key of the ciphertext is one bit of the ciphertext is changed, the entire one bit of the key is changed, the entire ciphertext will change. Right? There will be no pattern. Every pattern will be broken. So if I just change the 7th bit, that should not only the ciphertext every 7 bits got changed. It should not be the case. Everything, every bit position will change. If that happens, we call it confusion. Okay. And diffusion is the relationship between the plain text and the ciphertext. Even though there is one single bit of the plain text change, half of the ciphertext should change. That's what he said. One bit in the plain text should change half of the ciphertext. And with this, we have come to some lemmas. Lemma means that corollary of this principle. One is plain text key and ciphertext should be of the same length. Are you getting? Only we can achieve if plain text and ciphertext is of two different sizes. Then either from the plain text I can guess the ciphertext, or ciphertext to plain text, because that will not have an equal influence. They will have the same length. Guys who are online, you are following me?
Yes, sir.
Okay. And secondly, the key and the plain text will also have the same size. Then only key will have the equal, every bit of the key will have equal influence of the entire plain text or the ciphertext. Right? So this is, yeah.
So usually the message, we cannot say that it only be 8 bits of message. Right? So it depends on how much message you are like.
That's it. Oh, I just thought that it's yeah, I just thought it is a big thing.
So the question that I was asking was, usually the message that we send based on depends on the situation, right? So always the message is different, the message length is different. Will that be coming to the picture?
So you are saying we are using 128-bit key, but the message might be 1 gigabyte.
Yeah.
Right? Exactly. So that is
Ciphertext would be 1 gigabyte.
yes. Ciphertext will be 1 gigabyte, plain text will be gigabyte, but it is not following this one. The key is a shorter one, right? So yeah, that is a problem, because if key is as big as the plain text, then there is no point. Then I can keep the plain text secret only. Why should I spend on key to make the one? If I have to make 1 gigabyte of data secret, then I will make the plain text secret only. Why the key? There is no point of doing that, right? Yeah. So we have, that is a problem. But this is the mathematically proven that this will happen. But this is really not implementable. That's true. That Sharon also know. But he was a mathematician. He has to give the base mathematical
1 gigabyte of cipher will be
broken
broken into
into chunks, so that like if it is 128 bit key, that means entire gigabyte of data will be broken into 128 bit chunks. So that's how we implemented it. But still that will have a problem. I'll come to that. I will show that one. Okay. So this is the mathematical one. So if you really want to, do you want me to explain this thing, or we can leave it? You understood this notation, this formal notation? Okay. This is the length of the key, ciphertext and the plain text. Then it provides perfect secrecy only if every key is used equal probability of 1 by k. Okay, so that means it has equal influence of the entire ciphertext. The key has equal influence of the center. So this one, the first rule, this is in simple English I have written. So this is actually given by Shannon. So this we can read like this. This is the inference. But the mathematicians never speak in a simple language. We know that, right? So this is the complex one. That means it has an equal probability of 1 by k. That means it has every bit of the key has equal influence of the plain text. So that's why I have just translated this thing into simple English. So if we understand these two, it is fine. Probably if we are not comfortable, or if we are not familiar with this kind of notation, it will be the first time it will be little bit difficult for you to understand. So it is a priori probabilities he has used. So these are the properties of the secure cipher. So he has given. Now this one will just, we have to understand a little bit about this. So this is also a formal notation. Now it gives the definition of a crypto system. What is a crypto system? It says, now I'm just okay. Crypto system has 5 different things. It is a 5 tuple. 5 tuple means it has 5 different things. What are those things? First is the P is the plain text. So if we are using okay, just give me. I'm just finishing this one. Maybe another 3 minutes. 3 to 3. So this is getting mirrored. Okay.
Then it's fine. I see the current writing into left hand.
Okay, that way.
No, it's not clear.
The plain text is written as plain text, or it is written as.
No, sir, it's, for him it will show it because
This is B or this is B for the guys who are there.
So
The second one I see B.
Okay.
we see the first one.
Okay, then your.
Okay, it is connected to my.
Yes.
Okay.
But you can watch here only. Okay. P is plain text, all possible plain text.
In part, so that people can understand.
Okay. Sure. First is P is the plain text. Plain text means all possible plain text. That means if we are using English, A to Z, all possible combination. All combination between A to Z of infinite number will be the plain text. Cipher text will be the same, A to Z, all possible combination. Key space, if we are using 64 bit of key, then it is 2 power 64. Like actually this is the like all possible, like all the 2 power 64 different combination. All these things are the set of all 64, all the combinations of 64 bits, right? E is the encryption function, whatever functions we are using. So now we know it is all number. We know that cryptography, whatever we are calling cryptography, is no more just doing some circles with a cylinder, with a substitution of table or something like that. It is all a number. and it is kind of a function. Some functions we will apply on the plain text, we will get the ciphertext. So ciphertext equals to function on the plain text. Right? This function is called encryption function, and P is the function inverse of C. This is called decryption function. So I am writing C is the function of P. This thing is the encryption function. Decryption function is P is F inverse of P of C. So if I apply the inverse function of the ciphertext, I will get the plain text. So now it is simple mathematical functions. Now that function might be anything. That function might be cube, square, sine, right? Sine, cos, tan, anything. Anything. So which function is the good one as a for cryptography, that we need to find. If we can find, we are done with the cryptography. So far, these are the 5 things. We know what is plain text. We are anyway, if we are speaking in English, it is A to Z. A to Z, all possible combinations. Ciphertext, since we know the P, ciphertext will be also like A to Z, all possible combinations. K is the 2 power key size. Now, so far it is fine. Now we have to find the function, the encryption function and decryption function. If we can come up with a good mathematical function, we are done. We don't need anything. Okay? So we'll do that after that. Now you guys can connect, right? I started with a very basic thing, but now I am slowly going into the depth. Fine? Just let me know if you are losing track or if something is becoming too boring. Fine.
Encryption function is you apply the key in the function.
Okay. Actually, so I have just taken this one. Actually, this will be key and this will be key. Okay.
Function would be or and or
Anything, any mathematical function. Now we have to find that what is that base mathematical function which will provide this. Okay. So now it's simple. We know that in the black box level, we know what exactly we are going to do. If we can find the entire crypto system, we will get it. Is that the copy then?
copy zero.
Copy Z?
It was very copy. Okay, it is there.
Now it's getting old. Old copy.